All right. So now, since we have talked about stormwater quantity and quality, let's look a little bit at how stormwater quantity and quality looks. Now we have this graph here, and if I were to say this is flow, which is in, let's say, meters cubed per second or liters a second, over time, if we look at the flow discharge from a grassed area, as we have a little cloud that starts, this is the cloud, right? Let's say this is the cloud, and it starts, rain starts dropping from the cloud, and the rain looks like, I don't know, let's see, the rain is blue, and it looks like this, right? Not really a raindrop, but you guys get it. The rain falls. Maybe we'll make it a little bit less wide, a little bit shorter in time. You'll see why soon. All right. So it's raining, right? Well, at the time t0 when it starts raining, which is here, right? At this time, water goes into the ground and generates no flow. It's gonna make the ground a little bit more wet. But after a little bit of time on the ground, the water will generate some flow, and we typically represent it like this. Let's make it blue, and then like this. It's an isosceles triangle. This is, let's say, the period of time when at the time when you have grass. It's a pasture. Water falls on the ground. There's a little bit of delay because the ground sucks up some water, and then when the ground is wet, fully wet, it starts discharging an overland flow path, and water goes into the discharge point. Now, if we look at what happens when we pave all over the surface, what you have is a small amount of loss here at the first time, and then even for the same event, the discharge is higher. The reason why the discharge is higher, I think it gets, that's a good question. I think it discharges faster. Kind of looks like this. The reason why it discharges, so the discharge is higher because all this volume, so it's really important when you see a graph like this, always think about area under the curve. Area under the curve is one of the most important concepts that I can share with you today, because once you understand that flow multiplied by time is volume, then you start to get an idea about stormwater and how things happen, right? So this area under the curve, obviously this area here, minus this other area here, that would be how much water is sucked up by the ground, right? So this is the amount of water that gets stuck into the ground, and plants grow. Plants need water to grow. A lot of water gets stuck in the root zone. Some of the water goes down and recharges the aquifer. So the dynamics of a permeable area are quite different than the dynamics of an impermeable area. And it's important to understand that. And also, obviously, to look about things, another concept, dynamically or operationally. I like to say that a lot. In every, and this I feel works for every aspect of life. In every aspect of life, if you think about things dynamically or operationally, how this thing moves through time, this will have a really important role in helping you understand the world. As engineers, what we're trying to do, we're trying to understand the world. And I'll talk about that too. And as we try to understand the world is not static. Systems are dynamic, things move through time. And I know this seems, duh, of course, but a lot of times people don't think about things dynamically. And even more importantly, you will find that some of the calculations that we do, in those calculations, we don't think dynamically. So in terms of stormwater, if everything you want to do in relation to stormwater, my suggestion is just close your eyes, imagine you're a drop of water, you fall on this patch of soil with your siblings, brethren, cousins, your forefathers, and then your your children in time, and then what happens to you? What happens to your cousins and siblings? What happened to your to those who came before you, and what happens with those that would come after you? So if you're a drop of water that falls on the piece of land, on a grassy piece of land, what you're going to do is you're going to get probably stuck in the grass, in the soil there, but then those who come after you, well, you're already stuck in the soil, so they're not going to be able to get stuck in the soil gets saturated, and so on and so forth. All right, now you see there's a delay here. This delay happens again as the soil gets saturated. There's a small delay here because a small amount of water gets stuck into the interstitial spaces, and there's a little bit of water lost on the surface, even if it's concrete, right? About a millimeter. If you put water, or bottle of water, if you put it on the ground, just take it out on the road and just dump it on an asphalt road, you will see that it will not find its way to the gutter, because to the stormwater side entry pit or top entry pit, because it will just get stuck. It's just going to make the road a little bit wet. It's going to make a wet patch, but it's not going to create any discharge. That's the same concept. Sorry. All right. So for stormwater quantity, we have a concept either of time of concentration or critical storm. And what does that mean? That means that if you have let's say, a piece of land, let's go. This is the plan. We have a plan and we look at a piece of land. Ooh, let's make it black. And what we have on this piece of land, looking from the top in a plan view, we have like a big warehouse here, and then this is a car park. Let's just assume all of it is impermeable area. The warehouse in the middle and the car park around, and then here is the road, right? This road, this is the road. Let me move it this way, and then you have I don't know, the driveway is in here, right? Something like that. Right. So now what happens is the water that falls on this area will be moved very, very, very fast from this surface into the road, and I will show you how a IFD data table looks like. All right, so don't worry too much about things around. The important part is this IFD data table. What does this table say? The table say on the left you have a duration of the storm, and the columns are the probability that that storm is going to show up in a year. We used to say average recurrence interval, which was on average this rainfall will come once a year, once every 2 years, but now we call it annual exceedance probability. It's just statistical speak. For the intents and purposes of this exercise, just consider 50% AEP means it shows up once every 2 years. 20% AEP shows up once every 5 years. 10% once every 10 years. 5% once in 20 years. 2% one in 50 years. And 1% one shows up one time in 100 years. So you can see here where you have the values that, let's say if you have a 5-minute duration at once every 2 years, it's gonna, the millimeters a year the millimeters per millimeters an hour rainfall will be 66. But if the rainfall is shorter, then the intensity is higher. So the concept is that shorter intensities have higher rainfall, and longer intensity have shorter rainfalls have higher intensity, and longer rainfalls have lower intensity, which kind of makes sense. If it rains for half an hour, it's not going to rain with the same intensity as if it rains for 5 minutes. 5 minutes really big now. Half an hour not so big. Like it's big over time, but not so big in millimeters per hour in terms of intensity every minute. Now, this data table, I must tell you, is a lot of it is black magic. We don't have enough data to come up with this. This is just a statistical analysis. What people have done at the Bureau of Meteorology have taken a long data series or a continuous data rainfall over 30 years, and then they came up with this data table. But this data table is easy to use because when you go back to our drawing and you say, all right, when it was green, it looked like this. This was the rainfall that I was handling. Let's say the time of concentration is 15 minutes. Well, when we put everything in, we pave over everything, then the time of concentration will be shorter. So actually, this graph is for the same duration of rainfall as before, but now the time of concentration is shorter. So what you will really get will be something like this: a higher peak for a shorter time, because you're handling 5 minutes, because the rainfall that's going to generate the biggest flows is shorter. The concept is that you want to handle the biggest peaks. So this is a peak flow, right here. You want to handle the biggest peaks and drop them down in order to only have the biggest peak here, like this big, right? So the way you do that is let me maybe this one is a little bit confusing. Let me remove this. Problem kind of solved. So the way you handle this is you don't let anything go past, any peak go past this amount. And what you do, let's make it black. And what you do, okay. And what you do, you take this area under the curve here, and you stop it in a detention tank. So after you calculate and you manage your peak flow, the peak flow looks like a little bit like this. So your flow will look like this, right? Something like that. So all this area right here is moved under the curve, so the discharge from your site is not flooding anybody downstream, and this is done with an on-site detention tank. Now, a lot of this information is on our website. If you go to cleanstormwater.com.au, learn stuff. We have basic information, tells you a little bit who is this for, a little bit of context of why we do things. And if you go to core concepts, you will see the distinction between IFD data and continuous data. This information also, you can learn about it if you go to, you log in, sign up, and you go to the Stormgate portal, you use BOM the Builder, and BOM the Builder has some information here, which will help you learn about these things. And a few really good options to see, for example, rainfall, annual rainfall in Australia. So this is a heat map or a colored map, and this annual rainfall in Australia map, once it loads up, is going to show you kind of what you can expect as rainfall in Australia over time. And this is kind of where they generated the IFD data from, kind of part of it. Or this one was generated from the continuous data, but then they did some statistical analysis. This is they being ARNR. All right. Thank you very much.